Hi, good morning, and welcome to the ZP live streaming webinar on screen-printed electrodes. Just do a quick sound check to make sure I'm coming through okay. Yep, everything looks good there. Drop me a message if I'm having any audio or video problems. But that said, let me go forward. This is, as I say, live streaming, and we're going to talk about screen-printed electrodes this morning. So let's not have talk. Let's just do a quick summary of what we're up to. So we are going to talk about screen-printed electrodes. We are going to talk about essentially why you should care about screen-printed electrodes. We'll do some practical examples, and then we'll do some, when I say practical examples, a real-world example or use of screen-printed electrodes. And then I will also jump into doing some live demonstrations using screen-printed electrodes in front of you this morning. So there'll be an awful lot of content, commercial and technical, all mixed up together. So I'll talk about Sudan Red as a sort of practical example of use of screen-printed electrodes, a classical sort of ferricyanide experiment, but also how to clean screen-printed electrodes. And then I'll also do something called a sort of Randall-Sevich analysis of a screen-printed electrode. With that said, let me go forward with the slides. So I sort of start off with the kind of quick question, almost hyperbole as to, why should you even care sort of thing. Now, I'm pretty sure that you have a good sense of why we should care about screen-printed electrodes. But as I say, this is not one of those kind of webinars where it's all going to be talk. I'm actually going to do, live demonstrations. And so the first one is just to kind of build a context, especially for maybe people who are watching this video later on. Why should they care about screen-printed electrodes? So I think the sort of the most used biosensor in the world, probably after pH, let's say, is actually glucose strips. And these are a good example of why you should actually care about glucose sensors. Now, this should be quite fairly interesting because I've had my breakfast about half an hour ago. Now, what was nice about that is I hardly had a drop of blood that time. I didn't actually go very deeply. So there was, a very small drop of blood. And then there's my glucose reading, 123 milligrams per DL. Now, the reason I bring that up is because I'm asking the question, why should you even care about screen-printed electrodes? And I think the glucose strip, is the kind of the archetypical example of why you should care about them, because in fact, it's demonstrated that screen printing it's proven both electrochemistry as a science, but also it's supported by screen printed electrodes as a science that, you can scale this, you can make it low cost, you can make it easy to use. So when I talk about screen printed electrodes this morning, it's always going to be in the context of, because in the end, it can be commercialized. There's so many sort of technologies that one could pursue in one's career or in one's business, but this is one of those kind of technologies where actually, it is, screen printed electrodes in combination with electrochemistry could be low cost. They can be easy to use. I mean, I did that test just now. I got the result in, and it's actually also rapid result. When I say rapid result there, you saw that in fact I did that sample prep and test in 10 seconds. I did it. The analysis itself actually only took 5 seconds, but I had to sort of prick my finger, get that drop of blood, and then I took the reading. So why should you care about screen-printed electrodes? Because actually they've already demonstrated themselves to be a very good way of taking analytical sciences and putting them into the hands of people in a low cost, easy to use and rapid manner, which is what people really want. Diving a little bit deeper onto screen printed electrodes now, I've got our hypervalue carbon electrodes and I've got our 501 carbon electrode up here. So I just want to talk about a few points around screen printed electrodes. It's probably worth saying that there's a discount code at the end of this. So if you're interested in getting these, I'll give you a link and a discount code at the end of this webinar. Now, when it comes to materials, at ZP, we get lots of inquiries and people are interested in carbon electrodes. I put carbon/graphite there because we call them carbon electrodes. I think strictly speaking, the material is actually graphite in them. We get inquiries about gold, we get inquiries about platinum, we get inquiries about graphene. It's probably worth saying that when I was showing you that glucose test just a minute ago, it's probably worth saying that that was a sort of demonstration of low cost. Now, so my point is on this. The reason I'm bringing up low cost is because everyone uses gold electrodes, especially if they're building immunosensors. They're all reading the same papers, which is about self-assembled monolayers and the binding of a sulfur atom or sulfur group rather to a gold surface. And that's kind of very classical kind of science, self-assembled monolayers. The problem with it is it demands gold, and gold is something like tripled in price over the last few years. It's historically extremely high, and because whenever there's a kind of a financial crisis, everyone goes to gold. So when you're using gold as a material, you've got a kind of a conflict there, because you say, I want to make a low cost sensor. Oh, but by the way, I'm using gold, which everyone else wants to use gold because actually it's considered a kind of, a place of safety in financial crisis. People invest in gold. I don't think gold is a good choice when you're trying to make a low cost biosensor. And actually, if you do read a little bit deeper into the literature, when people are talking about making immunosensors, aptamer sensors on gold, you could have also done it on carbon. It's just, that it's easier to do it on gold because of the body of literature. So I think avoiding gold is a good idea. Platinum is not as always as easy to avoid, because sometimes platinum is because you're using a enzyme, and the enzyme may be an oxidase enzyme, and it may be therefore reacting with the target molecule, glucose, for example. Glucose through the enzyme reacts with oxygen and produces hydrogen peroxide, and then platinum is a good choice for that. So it's not always so easy to avoid platinum, but I do find that most people using screen-printed electrodes are actually not so interested in platinum. In fact, they're more likely to be asking, do you have carbon? Do you have gold? And actually, do you have graphene? Now, graphene for me, it's kind of this wonder material, but I don't really think it adds a lot of value to biosensors. Why do we have so many publications on graphene these days? It's because when you're producing new papers and you're trying to get into scientific journals, you have to show, that you're novel. And so once upon a time, people would have used single wall carbon nanotubes. Then they were, and multi-wall carbon nanotubes. But those have kind of gone out of favor, and now people are using graphene. But it will essentially be a fad that comes through, and then there'll be a new material will arise, and everyone will publish on graphene. So graphene, I think the reason it's used so much at this moment in literature is not because it's making the sensors or biosensors any better. It's because it's novel, and for a while there, it was easy to argue with scientific journals that your work was therefore novel. I think that novelty is definitely, it's over, let's say. It's not novel to now use graphene. So I would avoid graphene because actually it adds an expense, because you essentially, with the graphene processes, they're often taking a source of carbon, using some sort of an extra process on top of it and turning it into graphene, and it adds a cost. So it's my personal opinion, but stick to carbon and graphite if you can when developing biosensors, especially if you have any kind of vision on commercialization. People often come to us, and this is a big, let's say, problem in screen-printed electrodes, that everyone wants bespoke custom designs. The problem with custom designs is, I'll just hold up one of our sheets actually. Here's a sheet of 300 hypervalue carbon electrodes. There's so much engineering has gone into making these reproducible, the quality systems about them. And the fact that makes them quite so good is because we produce them all the time. If you want something to be good, you need to be doing it in a constant effort at quite high volume. And so in manufacturing, if I want something to be good, I can't be manufacturing it on occasions. I actually need to be manufacturing it all of the time. So the problem with customization is you may only need, let's say, 1,000 screen-printed electrodes, or even 10,000 screen-printed electrodes. So this sheet has got 300 electrodes on it. So if you come to us and say, oh, I want a really bespoke design, and how many do you need? I want 1,000. That's 3 sheets. It's not even worth turning the machine on for 3 sheets. You may say, oh, well, I want, 10,000. All right, well, 3 sheets became 30 sheets. 30 sheets is still nothing. You can appreciate, how thick that, 30 sheets is. It's absolutely nothing. So be very, very, very careful for asking for customization. I think you're much better off in your early days of R&D around the use of screen-printed electrodes is actually using off-the-shelf screen-printed electrodes. If the company's producing them properly, they should have quality systems in place. It's what we do. We sort of follow the processes very very meticulously, and we actually also do, at the end of our process, we also test all our electrodes or test a batch by voltammetry to make sure that they actually electrochemically perform the way they should. I think so many companies have gone into customization too early and then actually been trapped on this customized piece which only they want. There's not a robust quality system behind it, and it ends up, they don't pay much for it, but they pay a lot for it through the quality. I come across so many companies that only have a yield of 33% or 50% on that. Now, something about our designs is potentiostats are getting smaller. This is just a video I just put up on YouTube. You can kind of, if you go into our channel, you'll find it. But see this potentiostat in my hand? See how small that potentiostat is there. Potentiostats are getting smaller. A problem that's starting to appear in screen-printed electrodes is when people were using potentiostats that were, as big and mains powered, big boxes, there was all the power in those potentiostats than we would ever need. But now that potentiostats have got much smaller, actually people are starting to notice a sort of phenomena that at higher currents and higher potentials, they suddenly lose signal. And it's basically there's something that fails on that potentiostat called the compliance voltage. Now at ZP, we're quite used to making screen-printed electrodes, and we're also quite used to making very small potentiostats. So we actually understood this compliance voltage. So we actually have a problem that most people don't realize exists until they encounter it, is compliance voltage. And that's something that we've really sorted out on our screen-printed electrodes. As you can see, that potentiostat is tiny there. One of the things that really messes up the quality of signal in potentiostats, in screen-printed electrodes, is actually connectors. There was just a video I just did very recently where somebody's problem was actually the connector they had. It was leading to what looked like a lot of resistance in our screen-printed electrode, but they're using our screen-printed electrode with a third-party potentiostat, and the connectors were just not good enough. They weren't making a sort of a low resistance connection. They were actually making a high resistance connection. So if you are using ZP electrodes, just know that if people send us PowerPoints with kind of, this is my data and this is my setup, we're able to actually troubleshoot them. Now the response there was, oh, can we use your potentiostat? And I was like, well, yeah, you can use it, but unfortunately you do have to pay for it. I just want to give you a practical example of, so I'm just going to talk through this very quickly, but I'm going to take some screen-printed electrode technologies shortly. I'll put them onto the potentiostat. I will tell the potentiostat what to do through my phone. In fact, I'll even just change cameras for a second just so you can see what's coming. And I will tell the potentiostat essentially what to do using my phone. The potentiostat will give the data back to my app on my phone. And then, in fact, I'll send the data to a cloud system called Julie, where we'll process the data and give a signal back. So I've got the word demo here to remind me to actually do that demonstration. So let's take a screen-printed electrode technology. So this is what you already know, which is, why should you even be interested in screen-printed electrodes? It's because actually they are one of the best ways of getting real-world applications out there. So I'll take this potentiostat. I've got my phone in Bluetooth connection with it at the moment. I've labeled up the data so I can find it easy enough. So I've got Red Bull demo. So what I'm going to do is I'm just going to grab a real world sample. All right, so I've grabbed that real world sample. I'm just going to grab myself a sample tube, which I have done. Right, I'm just going to grab myself a actual sample out of that drink. So the nice thing is you can see everything live today, which also talks about, my confidence, let's say, in our Screen-Printed Electrodes. So I've got my sample here. Put the sample in like that. I will just grab some buffer, but it'll all be quick. It'll be more like that kind of glucose demonstration I did earlier on, where you know, electrochemistry has, I say, a couple of advantages. One of them is, I don't have to do much sample prep. In fact, I couldn't do an optical measurement on this because, in fact, it's actually full of bubbles because it's a carbonated drink. So electrochemistry doesn't care that this is a carbonated drink. I'm just going to do the sample prep. Watch me because it'll be quick. There we are, done. Right, now what I'm going to do is I'm going to advertise one of the other advantages of electrochemistry is, in fact, it only takes 50 microliters of sample. So remember when I did that drop of blood earlier on that glucose strip? There we go. I'll go back. I will go continue. I'll start measurement. And I can see real data arrive. I can see data arriving in real time here. In a minute, the real signal will kick in. That's a couple of extra molecules that are actually in that sample. And then there's the real caffeine signal there. Now that data then goes off to the cloud where we process the data and we give you an absolute perfect answer. You can sort of, if you ask maybe ChatGPT, what's the concentration of caffeine in milligrams per gram in Red Bull? It should say 0.3 milligrams per gram. So I've got your 0.259, but if you round 0.259 to the nearest decimal point, there's 0.3 milligrams per gram. On the side of the can, it says 0.03%, by the way, but I've been, obviously a chemist, so I could convert percentages into milligrams per gram. So that's a perfect answer. Now, the reason I got the perfect answer there is there's something that we're doing at Zimmer Pico that really is hard to do in screen-printed electrodes. It's actually make reproducible screen-printed electrodes. Biggest problem in screen-printed electrodes, especially those that are entering the R&D community, is reproducibility of screen-printed electrodes. People think that all their experimental variation is due to them, but it's actually the underlying screen-printed electrode that's actually the problem. I just want to show you something else that we have at ZP. So let me just indulge me for a second while I share my screen with you. So I'll go to here. This is the Julie system. So when I was using the app earlier on, the app said, oh, upload complete. It gave me a result, but it also said upload complete. And I can see the results here as well. So here's the result. This is a very powerful potentiostat because, it's cloud enabled, which means, that we can, I don't need to go hunting around for my data. It's up in the cloud. I can see the result here. We've got feature extraction built in. So we've extracted the peak height and we've turned that into milligrams per gram. So pretty powerful. Now let's get back to the reason why you're here, which is not me rabbiting away. It's actually getting some more demos done. So I do want to do a demonstration on Sudan red in a minute. I do want to do a demonstration on ferricyanide in a minute. And I want to just do a last one, which is looking at the Randall-Savage analysis as well. Randall-Savage analysis just kind of says that peak height in cyclic voltammetry is proportional to the square root of the scan rate. This is something that people learn as undergraduates. If they do electrochemistry, that is as undergraduate, but definitely when you're doing postgraduate studies on electrochemistry, it's something that is definitely kind of coming up. The first thing I'll do is actually Sudan red. And the reason I'm sort of slightly interested in Sudan red is because it is used to enhance the colors of things like spices and palm oil. But unfortunately, I mean, it shouldn't be used because it's actually carcinogenic. Now, electrochemistry is a good way of doing detection of molecules, including these kind of dyes. We'll do the voltammetry, so we're going to treat it almost like a purely academic exercise. But just know that what we call this when I oxidize this is really a EC mechanism. And now what I mean by that is that there's a bond in an azo dye. There's an azo group here. The bond gets oxidatively broken. So we got an electrochemical process, then followed by a chemical process. And it's basically irreversible. And you'll see that irreversibility in the data when I actually gather it live for you. So what I'm going to do for a second now is I'm just going to stop sharing that for a second. I'm just going to change cameras over to here. I will take Screen-Printed Electrode from Zimmer Peacock. I'll click it in there. That's really good way of making connection, by the way. You can sort of see I'm not slotting it in. Slotting things in, by the way, can end up damaging the electrode. So that didn't require slotting. It just required clicking up like that. I'm just going to grab I'm just going to grab a sheet, which I've done. I've got these QR codes in front of me because I actually want to change modality now. I want this potentiostat to actually work with cyclovoltammetry. So I'm just going to scan that QR code. Yeah, I'm in cyclovoltammetry mode. And I'm going to get a sample of Sudan red. So I've got a sample there. And I'm just going to, again, get 50 microliters. Now what I'll do is I'm just going to give this a name so we can find it shortly. Everything's live, by the way, so sometimes you'll even see me adjust settings. If the voltammetry is not good enough, I will adjust settings. So what I'm going to do is I've got some settings here, and what I will do is I'll start at minus 200 millivolts. I'll probably scan to 1,000 millivolts. I'll go quite fast, by the way. Classically, people love to do slow voltammetry because it gives them beautiful data. But if you're developing real-world applications, people really do not want to be waiting around for a long time for your assay to run. So I've kind of done some conditions there. I'll just go back and I'll put the sample on there. You'll keep hearing me say 50 microliters. It's enough. 50 microliters is enough to cover our Screen-Printed electrode. There we go, one drop. That's one of the advantages of using Screen-Printed electrodes, by the way, is that especially when the sample is kind of valuable, which is often in the medical space, you know, drops of blood, and people are not that willing to give you blood. And then I hit start measurement, and off we go. So I'm kind of getting a baseline here. I get the raw signal in real time, and then we'll see. And if I don't get the signal, then I will adjust. I've noticed this before, actually, a little sort of oxidation. In fact, that is the oxidation of the material. And then it's doing the second scan. Sorry, it's doing the reverse scan. So I will bring up so it then says upload complete. So what I'll now do is I'm just going to have a quick look at that data again in the cloud. So I'll just share my screen with you. Go to here. That was the caffeine data that we did earlier on. Now I'm looking for a report called, I think, Sudan. Let's have a quick look. There it is. And anyway, I can see the oxidation of the Sudan red there. So I don't have that higher concentration. In fact, I can see here what I should have done is I put it on a current range of 100 microamps, and I should have maybe put that on a current range of 10 microamps. But I have got the oxidation here of Sudan red. Now what I'm going to do now is I'm just going to go back to my slides to remind myself, and that was an EC mechanism. I didn't get the reverse on that. So when I kind of look for the reverse peak, let's say, I see the oxidation, I don't see the reduction, and it's because it's irreversible, because there's this chemical reaction following the electrochemical oxidation, which prevents me from doing a further reduction. Side note, if I did a really fast scan rate, I may have actually been able to do the reduction, but I did 100 millivolts per second, and it wasn't fast enough to be able to see the reduction. Now what I'm going to do now is just go slightly into a more classical experiment, which is really the oxidation of ferricyanide. I'm sure you've done it, and if you haven't, you may have seen videos on it, but I will talk about it very quickly, and then I'll actually do it. And I will obviously do it on our Screen-Printed electrodes. So cyclovoltammetry of ferricyanide. We use a triangular waveform. We have a beginning potential, we have an end potential, and then if we're doing cyclic voltammetry, then we'll return to the beginning potential. And I'll have a solution of ferricyanide. because I'm starting at a negative potential, the ferricyanide will immediately become ferrocyanide. So you'll actually see the oxidation of ferrocyanide to ferricyanide, even though I put ferricyanide in there, but because I start at minus 200 millivolts, it will immediately convert anything near the surface to ferrocyanide. So I will actually get the oxidation. Now, this is just an E mechanism, just an electrochemical mechanism. There's not this EC mechanism, so I should be able to get reversibility out of this. So I'll have my conditions. I'll probably put these conditions into the app just to remind myself. That will be the electrode I use, and I'll do it there. And what I'm going to do is I'm going to do 3 experiments now. I'm going to do a fresh electrode, and then I'm going to clean the electrode, and then I'm going to do the experiment again. I think this is an important, let's say, point. So let me just stop sharing for a second. Let me change cameras. So I'm going to do it without cleaning, then I'm going to clean, and then we will do the experiment again. So I've got my potentiostat. I'll take that electrode off. I will take an electrode and put it on there. I've got some 5 millimolar ferricyanide here. I will take, again, I love to be consistent, 50 microliters of solution, and I'll put that on there now. So 50 microliters of 5 millimolar ferricyanide. I'm just going to go to the app and do some settings. You will see me again do a fast scan rate. I'd say I'm definitely doing faster scan rates than academics would otherwise suggest, because if you're going to make a real world assay, nobody wants to be hanging around, right? So ferricyanide is what this is. So we'll be able to find this ferricyanide, 5 millimolar, right? And then I'll go to conditions, right? So I'll start at minus 600, but in fact, I will, I'll go to 600, sorry, just because I'm using the wrong thumb. I'll go to 600 millivolts. I've got 100 millivolts per second. I will leave it on 100 microamps, and I will now gonna hit start measurement. So I'll try. Right, so this is without cleaning, okay? This is just an electrode as received. And as again, this will only take, as I say, about 19 seconds, because don't develop assays which are intrinsically slow if you can. I mean, we try to make our assays run, 2 minutes or less, because people can wait 2 minutes, but people can't wait. People don't really want to wait 20 minutes. So it says upload complete. So we can go and have a look at that data in there. So I'm just going to share my screen with you, which I will do. So let's go and look for that data, reports, quick refresh. Badly spelt ferricyanide. But there's the data, and there we go. But now I want to improve this data. So what I'm going to do is just going to grab a cloth. In fact, have I got here? Yeah. Right. What I'm going to do is I'm going to take that solution off. So I'll stop sharing just so you can have a slightly better vision on my. I'm going to take that solution away. Right, so you see me take that solution away. I'm going to clean it with, you can use pH 1 or pH 2. I tend to use pH 2 because I've got what's available. I've got something I've got a solution that's available to me. And what I'm going to do is I'm going to just put 50 microliters onto that electrode. So I'm putting a non-ferricyanide solution onto here. It's a pH 2 acidic solution. So you can basically sort of mild acid, it depends on your perspective. So I'll put 50 microliters onto that, which I have done. I'm just going to change settings now. So this is a cleaning step. So I'll call that cleaning. I'm not super interested in this data. I'm just using it as a cleaning step. I suppose that's one of the powers of electrochemistry, that I can use it both as an analytical technique, but also as a processing technique. So I'm going to start at -1 volts, go to 100 volts. I may regret this. No, I'll put in 2 scan. Oh, no, oh yeah, I'll put in 1 scan. Let's just do 1 scan. Okay, so -1 volt to +1 volt, 100 millivolts, repeats of 1, just 1 scan basically. And I'm not so, it doesn't matter about the current range so much because I'm not actually that interested in looking at the data. I'm glad I only went for 1 scan, because even this is then 40 seconds. So we're just scanning, but I'm scanning just to basically clean the electrode. You will find on our YouTube channel and also our LinkedIn channel that I have started talking about cleaning screen-printed electrodes. I think it's quite rare to find anyone talking about screen-printed electrodes. But now that I'm starting to talk about it a bit more, I realize it's obvious, because when you've got everyone says, oh, glassy carbon electrodes, these are analytical electrodes, they've got a reputation for being good quality. The first thing you do with a glassy carbon electrode is you clean it. And so you're trying to hold screen-printed electrodes to the same, let's say, standard as a glassy carbon electrode, except with a glassy carbon electrode, you actually you clean it. And why do we not do the same with screen-printed electrodes? So I've now cleaned that electrode. What I now want to do is I'll take off that that solution. Easy enough to just do that. I will get 50 microliters of ferricyanide. I'll put that on there. There we go. By the way, you don't have to make detailed notes. I'll send you a recording of this afterwards. I'm just going to call this after cleaning. After cleaning, badly spelt, ferricyanide, just so we can find it, ferricyanide. All right, and then I'll go continue. I want to start at -200 millivolts. I want to go to 600 millivolts. 100 millivolts per second is fine. The scan, whoops, I only want 1 scan. Right, I'll hit start measurement and off we go. Now, don't forget, I've only done 1 cleaning on this electrode, so I didn't actually over clean it, let's say. But here comes the oxidation wave. In a minute, we'll get the reduction, because this is an E mechanism. It's sort of reversible, and upload complete. So let's just have a quick look at that. So what I'm now going to do is share my screen. I will go to here. Okay, so this was before cleaning, and this, I'll just do a quick refresh here. And then I've got the cleaning step, then I've got the after cleaning. So just have a quick look at after cleaning, but I'll also show you a little feature here where I'm actually able to compare the two anyway. Oh, look at that. That's such a difference. I think I almost should finish with that. What's the biggest problem with screen-printed electrodes? People complain about the quality, but I think that even if I'm manufacturing, it's okay to have workflows where, in fact, one of my workflows is cleaning. How many times in manufacturing would you have a cleaning step? I'm just thinking generically. And I can think of most processes where you're manufacturing, at some point somebody's degreasing or decleaning. But let's just have a look. Let's just do a comparison about how how improved that really is. By the way, ZPs manufacture those electrodes. I am not criticizing ZP, but it's not at all. But what it is that you actually, people don't really realize, and I should also emphasize the way we actually ship as well. We're shipping in these black bags, so we're really trying to take care of, lots of, A, keep them sealed, but B, keep things like light off them. So you can really know that we do actually think about this stuff quite a lot. But anyway, having a cleaning step as part of a manufacturing process or just before reading is actually okay. Let me just do a quick combine reports, which I'll do now. So I'm generating basically a third report of those 2 reports, where I'm putting, I'll go into tools. Yeah, so I got my data there, which is good. I just want to kind of look at the data quickly, which is good. So I'll shut that down, and it's extracting the data. And then, so this is the difference. Look at what, look what look what cleaning has done to my data. So I've come from the orange line to the green line. So just a quick trick. If you want to improve your publication, it's okay to, and if you were using glassy carbon electrode, you would have done this anyway, but if you want to improve, you can just see that a quick cleaning step improves. And I didn't, all of that has taken me the last sort of 5 minutes, let's say, with a lot with chat going on in the meantime as well. So almost there, but I just want to kind of, the last thing I want to just cover is Randall-Savich. I know this is about screen-printed electrodes, but so many people like to characterize screen-printed electrodes using the Randall-Savich equation. In the Randall-Savich equation, it kind of says that, look, that peak height for example, the oxidation of ferrocyanide to ferricyanide, that peak height is proportional to the square root of scan rate. And so if you plot current versus square root of scan rate, you should get a linear line. If you plot peak current versus just scan rate, then the kind of line starts sharp and then plateaus off. I've got another slide here. I'm just going to scan that QR code. So in fact, what I will do is I'm going to scan that QR code. I'm going to run, I'll grab some data and I'll analyze the data as well. So I'm just going to tell you that I'm going to run some scans at different scan rates, load the data up, analyze the data. So let me just stop sharing for a second. Let me just go to here. Let me grab my trusty app. I'm just going to scan a new QR code. Yep, so I've scanned that QR code. So I've got that. I will name this data now Randall Dev Chick. Right, that'll do. Right, okay. Right, so in fact, I've still got the 5 millimolar ferricyanide solution on there, in fact. So there's in fact no need to take that off or do that again. But what I want to show you is this, that what's the most valuable thing, and I appreciate you giving it to me, this one, what's the most valuable resource that you have in your life? It's actually your time, nothing else. Well, your family and your time, let's say, So what I want to say is, I just want to go continue, and we'll see what happens now. So it's loaded it, place the sample, lock the sample, start the measurement, start measurement. So this is actually, through that one QR code now, it's going to run a series of experiments. And this is the power of, let's say, electrochemistry, but also the particular power of this particular potentiostat, that I want to do a series of Randall-Savich type analysis. So this at the moment doing 50 millivolts per second. I think then it'll do 100, maybe 200, and then 300. So these experiments will get progressively faster because they're different scan rates. But I'm basically telling you how I can actually design a series of experiments and analysis and reduce it all down to one QR code, and then just automate the whole process like that, especially if you're kind of, if it's a manufacturing thing, or you have an assay that you need to roll out to real people. So it's doing all those experiments now, and they get progressively faster because the scan rate is progressively faster. Then it will have to upload all of those data to the cloud, and then it will analyze it in the clouds, and I'll be able to show you that real-time data. So now it's uploading it, and there we go, upload complete. We live in a very, very fortunate time that, in fact, you could appreciate that the demonstration I just did wasn't even possible 10 years ago. I mean, just the QR code is only something that's really come around in the last 2 to 5 years. Right, what I want to do then is just share my screen with you. I use the QR code, I use the ferricyanide solution. I actually did about 4 scans at different scan rates. Let's have a look at the data. So let's come out of here. Let's go and have a quick refresh here. I'll just save that for a second, not that I really need it. It says incomplete because I haven't put all the details in for the experiment, but you're not forced to. It's just a reminder. All right, go to reports. I can see the Randall-Savich is already up there, which is the one I just ran. Oops, a daisy, here it comes. So here's my data now, different scan rates, and then it's also plotted. It's also plotted the data, and this is the square root of the scan rate here. So it's already plotted the data, and so I've got an excellent fit to theory. It's not people use this kind of analysis a lot when publishing papers. All it really tells you, it doesn't tell you as much about your electrode. It actually tells you more about your process. It tells me that ferricyanide, when oxidized using cyclovoltammetry at a screen-printed electrode, is diffusion controlled. That's what it tells me. People mistake it for telling them something about the electrode itself. It's indicative of the electrode, but it's really telling you more about the diffusional processes of ferricyanide. But people are very much in love with it, and they use it a lot. I think it's really because it's just a simple experiment to do. You know, I did that in 5 minutes. It gives me a nice graph. I can publish with it. You know, so I think that's why people kind of stick to it. And there you are. You've got nice looking data like that. So let me go back to my slides just to remind me. Right. So I'm going to wrap up now because these were set to be 45-minute webinars. So what we see today, I don't need to persuade you, convince you that screen-printed electrodes is a good technology, especially if you're trying to, in the end, have your science be impactful. The glucose strips really demonstrate that. I've demonstrated a real-world sample actually where I was able to measure the caffeine in this using printing technology from Zimmer and Peacock and using a potentiostat. You also saw me use the same potentiostat to actually go on and do the oxidation of Sudan red. That was irreversible. Ferricyanide, which is reversible. And then I also did that Ranald-Sevich analysis, which you will find in tens of thousands of papers. But don't, you know, you saw, you know, what did it take me to do that? And that to gather that data took me 2 minutes. So it's a very quick way of, let's say, getting publishable data as well. Use that discount code. So if you use our web shop, shop.zimmerpeacock.com, and you put in 10% underscore May 10% May 2025, then you will get a discount for May. I think with that, I want to say thank you. If you have any questions, you've got my email anyway, because I would have emailed you to invite you. But if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.